Okay, so let's recall what an inner product is on a vector space. So an inner product on a real vector space V is a function from pairs of vectors, so the set of V cross V, into R that satisfies the following properties. And we usually just write the function as parentheses between V comma W. So this is my function. And the properties it has to satisfy are the following, such that, first of all, this is bilinear. And what that means is, for all W in V, the function that sends V to V comma W is linear from V to R. That is, once you fix this vector W, this is just a function of the first variable V, and this is a real number. So for every vector V, you get a real number. This is a function from V to R, and it's a linear function. Similarly, for all V in V, the function that sends the vector W to V comma W, so V is fixed, so for every W, this gives a real number. This is also a linear function from V to W. So this is the definition of bilinear. VW is symmetric. That means that for any vectors V and W, V comma W is the same as W comma V. And third, VW is positive definite. That means for all vectors V not equal to 0, the inner product of V with itself is always strictly positive. And a function, a real valued function from V on V cross V is an inner product if it satisfies these three properties. It's bilinear, it's symmetric, and it's positive definite. And what we call the length of the vector V is, well, the inner product of V with itself is positive, so you can always take the square root. If V is 0, this is 0, and the square root of 0 is 0. So this is what we call the length of V, and this is the notation for it. We say that vectors V and W are perpendicular or orthogonal or normal to each other. These are just three words in common usage. If the inner product of V and W is 0. Let me just show why this is familiar from, let's say, high school algebra. You remember that if two lines in the plane are perpendicular to each other, then the product of their slopes is -1. So suppose we take a vector v, say it has coordinates AB. And we take another vector w, and it has coordinates CD. So what's the equation of this line? Well, you go over A and up B. This is the line y equals B over AX. And what's the equation of this line? This line is y equals D over CX. So these lines are perpendicular if and only if the product of their slopes, this has slope B over A, this has slope D over C, is -1, which is the same as saying that BD equals -AC, or AC plus BD equals 0, which is the same as saying if I take the inner product of V and W, here's V, here's W, the standard inner product, you multiply coordinates and add AC plus BD. So saying that the inner product of these two vectors is 0 is exactly the same as saying the slopes of the lines they define is -1, is exactly the same thing as saying that these lines are perpendicular. So what you learned in high school algebra carries over to linear algebra. So we proved the lemma. Well, I don't know if I proved it, I'll prove it now. The lemma, for first of all, we say a set S of vectors is said to be orthogonal if the inner product of V and W is 0 for all vectors V, W, and S, V different from W. So if you have a set of vectors that are mutually orthogonal or mutually perpendicular, we say the set is orthogonal. If S is, or let's say a set S is called orthonormal, if first S is orthogonal, and second, every vector V in S is a unit vector. That means the length of V is 1. So a unit vector is a vector of length 1. Now, to make the following observation, what happens to a vector, the length of a vector, if you multiply it by C? So that C be any real number. Suppose I want to calculate the length of C times V. So maybe first I'll calculate the length of C times V squared. That's the inner product of CV with CV. because this is bilinear, I can take out this C. This is C times VCV. And again, because the inner product is bilinear, I can take out the other C. I get C squared VV, which is C squared times the length of V squared. So if I take the length of CV, that's the square root of the length of CV squared. That's the square root of C squared times the length of V squared. C can be positive or negative, but when you take the square root of C squared, you get the absolute value of C. The length of V is always not negative, so this is the length of V. So the absolute value, the length of C times V is the absolute value of C times V. And if V is not 0, suppose we let C be the length of V, 1 over the length of V. If V is not 0, the length of V is positive. So, and let U, the vector U, be the scalar 1 over the length of V times V. So then the length of U is the length of 1 over the length of V times V. You can take this positive scalar outside. This is 1 over the length of V times the length of V, which is 1. So U is a unit vector. So if you take any vector non-zero and divide by its length, you get a unit vector. Now, what is interesting is when you have an orthonormal basis. So we have the following lemma. So V is an n-dimensional real vector space. And suppose we let E1, E2 up to E sub n be an orthonormal basis for V. So that means this is, first of all, it's a basis. So this is a linearly independent set of vectors that spans the vector space. Every vector is a linear combination of these. And orthonormal means every two of them are perpendicular and the length of each is 1. So orthonormal is the same as saying the inner product of EI and EJ, that's equal to 0 if I is different from J. If I equals J, this is the length of EI squared. But if it's orthonormal, every one of these vectors has length 1, so it's 1 if I equals J, which is exactly this function I've called delta ij, which is called the Kronecker delta. This function is defined to be 1 if I equals J and 0 otherwise. So let V and W be in V. So V is some linear combination of the basis vectors. W is some linear combination of the basis vectors. And if I take the inner product of V and W, that summation I goes from 1 up to n xi ei times summation j goes from 1 up to n yj ej. If I expand this using the bilinearity, first of all, here I have a sum of scalar multiples of ei. So this is summation I goes from 1 up to n xi times the inner product of xi with this vector. And when again I expand this using bilinearity, this is summation I goes from 1 up to n, summation j goes from 1 up to n. I have xi, yj, ei, ej. But this inner product of ei and ej, this is the Kronecker delta, delta ij. This is 0 unless I equals j. And when I equals j, it's 1. So this turns out to be simply summation xi, yi, I going from 1 up to n. Now, if v is summation xi, ei, what that means is what we call the coordinate vector of v with respect to this basis e is x1 up to xn. And if w has this expansion with respect to the basis, w has coordinate vector y1 up to yn with respect to this basis. So if I have an orthonormal basis and I write every vector, if I represent every vector by its coordinate vector, the inner product of v and w is just the standard inner product of this vector in Rn and this vector in Rn. So linear algebra in an inner product space becomes very familiar if you have an orthonormal basis. And the question is, given a finite dimensional vector space, can you construct an orthonormal basis for it? And if so, how do you do it? So there is a way to do it, and it uses what is called the Gram-Schmidt orthonormalization process or algorithm. And it starts with a little bit of geometry. Suppose you have a vector w and a vector v, and I want to do what you might have seen a lot if you took elementary physics. You have, imagine you could drop the perpendicular from v to this line w. So this, which I'll put in green. Oops, that wasn't green. Try this. This vector I'll call it v1. So v1 is going to be a vector parallel to w, and we're going to call v1 will be the component of v in the direction w, and this vector I'll call v2. v2 is the component of v perpendicular or orthogonal or normal to w, and I've decomposed v into v1 plus v2. So given a vector v and a non-zero vector w, two non-zero vectors v and w, I want to decompose v into a part parallel to w and a part perpendicular to w. And you remember two non-zero vectors are parallel if one is a scalar multiple of the other, and two vectors are orthogonal or perpendicular if their inner product is 0. So how do we make this decomposition? Well, let me get a decent piece of paper for this. Here's W. Here's V. I want this vector to be V1, this vector to be V2. So one vector parallel to W would be the following. V1 is going to be a certain scalar multiple of W, and I take the inner product of V and W divided by the length of W squared. So this is a scalar times W. So V1 certainly is parallel to W because it's just some number, and this is a number. VW inner product, that's a number, length of W squared. Yeah. And I want V to be V1 plus V2. So the only way that can happen is if V2 is V minus V1. So suppose I let V2 be V minus V1, which is V minus the inner product of V and W over the length of W squared times W. So what I know is this vector V1 is parallel to W because it's a scalar multiple. This vector V2, just by definition, satisfies V equals V1 plus V2, right? So I must show that V2 is orthogonal or perpendicular to W, which means I have to compute the inner product and see if it's 0. So what is the inner product of V2 and W? Well, V2 is V minus VW over length of W squared times W. That's V2. Inner product with W. And by the bilinearity, this is the inner product of V and W minus the scalar times the inner product of W with W. But the inner product of a vector with itself is by definition the length of the vector squared. This is VW minus VW over the length of W squared times the length of W squared. And these cancel. So I'm left with just VW minus VW, which is 0. So by this magic formula, I have V is the sum of a vector parallel to W and a vector perpendicular to W. And of course, you might ask, well, can it be done in some other way? And the answer is no, because this decomposition is unique. So what we have first is V1 equal to the inner product of V and W divided by the length of W squared times W. and V2 equal to V minus VW length of W squared times W. So we have V1 parallel to W, V2 orthogonal or perpendicular to W. And let's imagine we could do this in a different way. So suppose we have vectors V1 prime and V2 prime such that V1 prime is parallel to W, V2 prime is perpendicular to W, and V is equal to V1 prime plus V2 prime. So in fact, we have two decompositions. We have this decomposition, whatever it is, and we have our original decomposition, V equals V1 plus V2. So V is V1 plus V2, well, these are these two vectors. And here I have another pair of vectors, one parallel and one perpendicular to W. We have V is V1 plus V2 plus equals V1 prime plus V2 prime. So if I rearrange that, I have V1 minus V1 prime is V2 prime minus V2. But now we have something very interesting. So V1 and V1 prime parallel to W means V1 minus V prime is parallel to W because each of these is a scalar multiple of W, so is their difference. And V2 and V2 prime and V2 perpendicular to W means that the inner product of V2 prime minus V2 and W, again by bilinearity, this is V2 prime minus V2 prime W minus V2 W. But each of V2 and V2 prime are perpendicular to W, so each of these inner products is 0, and 0 minus 0 is 0. So I have two vectors, but they're the same. So let me just call this maybe V star. So V star is both parallel to W and orthogonal to W, perpendicular to W. And whenever you have a non-zero vector, the only vector that is simultaneously parallel and perpendicular to it is 0. So V star is 0. That's a lemma, which I wrote down in the notes at least. So that's equal to 0, which means V1 equals V1 prime and V2 equals V2 prime. This is just telling us the interesting fact that if you decompose a vector into a piece parallel to W and another piece perpendicular to W, those components in the parallel and perpendicular directions are unique. You only can do it in one possible way. So see, I'm trying to build up to the construction of an orthonormal basis. So this is in the current version of my notes. I'll post them later tonight. Let V be a vector space. W a subspace. And let W1 up to WK be an orthogonal basis for W. So here's my vector space. Here's W. And in W, I have this basis W1 up to WK. Now, if W is different from V, there's some vector W prime in V, but not in W. So if W is not equal to V, there exists a vector W prime, which is in V, but it's not in W. It's in the complement of W and V. And suppose I let W prime be the subspace of V generated by these original K vectors and W prime. So inside of V now, I have a bigger subspace, W prime. And the lemma says there exists a vector WK plus 1 in W prime, such that if I replace W prime with WK plus 1, W1 up to WK and WK plus 1 is an orthogonal basis for W prime. And the way we do that is, so I want to have a vector which is orthogonal, such that this larger set is orthogonal. So we know Wi, Wj, the inner product is 0 whenever I is different from j, and I and j are between 1 and n. Because the set from W up to 1 and k. Because the set of this, my original K vectors, is orthogonal. So in order for this larger set to be orthogonal, I must show, or I must construct WK plus 1 such that the inner product of Wi and WK plus 1 is 0 for all I going from 1 up to k. Now, I know how to find the component of W prime in the direction of one vector so that it's perpendicular to that vector. But how do I find the component of W prime so it's perpendicular to all K vectors? Well, one sort of naive thing to try is for every vector Wi from 1 to k, subtract the component of W prime in the direction of Wi. So for all j from 1 to k, the component of W prime perpendicular or orthogonal to Wj is W prime minus the inner product of W prime and Wj over the length of Wj squared times Wj. Right. So the component of W prime parallel to Wj is this, and W prime minus this is the component of W prime perpendicular to Wj. And what I'm going to do is just subtract all of these components and see what happens. So that Wk plus 1 be equal to W prime minus, let me call this I, all of these components. Summation, I goes from 1 up to k, W prime Wj in a product over the length of Wj squared Wj. So your picture might be something like this. Here we have W1 and W2, and they're perpendicular to each other. And then we have some vector W prime, which is not in the plane generated by W1, W2. And we want to find a component of W prime that's sort of perpendicular to both of these at the same time. So we know W prime minus this for I equal to 1 is perpendicular to W1, and this for I equal 2 is perpendicular to W2. Let's see what happens. So I claim that Wk plus 1 is perpendicular to Wj for all j from 1 up to k. So let's do this calculation. The inner product of Wk plus 1 and Wj, Wk plus 1 is W prime minus the sum. I goes from 1 up to k. W prime Wi inner product over the length of Wi squared times the vector Wi. And we're taking the inner product of that with Wj. So this is one complicated looking vector, and this is my Wj. So let me just use bilinearity. This is the inner product of W prime and Wj minus the sum minus all this inner product with Wj. So that's the sum. I goes from 1 to k, W prime Wi over the length of Wi squared, the inner product of Wi and Wj. Now, what is this? Well, if I is different from j, that means that Wi, Wj is 0, because W1 up to Wk are linearly independent. So the only time you get a non-zero term is when j equals I. And in that case, this is the inner product of W prime and Wj minus, you only have the case when I equals j, so this is W prime Wj over the length of Wj squared. When I equals j, this is the length of Wj squared. These cancel, and then these cancel, and we get 0. So this is a very important calculation, and if you think hard about it, you'll see this really gives us a way to construct an orthogonal basis for any finite dimensional vector space. Because what you do is the following. Here's a vector space V. So take a vector W1 in V not equal to 0. So that generates a one-dimensional subspace. I'll call it W1. If V is not one-dimensional, then there's a vector W2 which is not in this subspace W1. So I'll call it W2 prime. So choose W2 prime in W, but not in W1. W1 will be the subspace generated by this vector W1. So by the previous lemma, there exists a vector W2 such that W1 and W2 are orthogonal. And I guess what I should have said also when I was proving this previous lemma, here's the previous lemma. I said, take a vector space V, take a subspace W, let W1 up to WK be an orthogonal basis for W. And if W isn't the whole space V, you can find a vector W prime. So W prime is not in W. And we can let W, capital W prime, be the subspace generated by these K vectors and this new vector W prime. And then we constructed a vector WK plus 1, which was perpendicular to all of these guys. And what was the vector WK plus 1? The vector WK plus 1 was this vector. It was W prime minus the sum, a linear combination of W1 up to WK. So you can represent W prime as a linear combination of W1 up to WK and WK plus 1. So any linear combination of W prime and the K vectors in the original basis is also a linear combination of WK plus 1 and those K vectors. So W1 up to WK and WK plus 1 is a basis for this larger subspace, and it's orthogonal. So I can find a W2 such that W1 and W2 are orthogonal, and in the subspace W2 generated by W1 and W2 prime, in that same subspace is also generated by W1 and W2. And then I could say the following. So let, I don't know, W1 up to WK be a maximal, that is the largest possible subset of V that is orthogonal. The vectors are mutually perpendicular and linearly independent. Call that WK. If WK is not, I claim WK is all of V, so I actually have an orthogonal basis. Because if WK were not equal to V, then you can choose a vector W prime that's in V and not in WK. And then we get a vector WK plus 1 such that W1 up to WK plus 1 is orthogonal. And every orthogonal set of vectors is linearly independent. But I have a contradiction because a maximal set of orthogonal linearly independent vectors was this set of K, and now I have one with K plus 1. So this has to be a basis for V. And why is it that I said that an orthogonal set of vectors has to be linearly independent? So this is a little theorem, I guess. Every orthogonal set of vectors is linearly independent. And the proof might go as follows. So let W1 up to WK be orthogonal. Let C1 up to CK be scalars, real numbers, such that summation C sub I WI is 0. Suppose some linear combination of these K vectors is 0. Then if I take the inner product of 0 with, let's say, one of these vectors Wj, the inner product of 0 with any vector is the number 0. Of course, 0 is this. 0 is summation Ci inner product with Wj. And by linearity or bilinearity, this is summation I goes from 1 up to k, C sub I, inner product of Wi with Wj. But these vectors are orthogonal. So Wi Wj is 0 unless I equals j. So this is Cj, Wj comma Wj, because all the other terms are 0. This is Cj times the length of Wj squared. These are non-zero vectors. So this is different from 0. So Cj equals 0 for all j implies that the set is linearly independent. So this gives us a recipe to construct an orthogonal set of vectors. And let's do an example. So in the plane, suppose we have the vector 2, 1 and the vector 1, 2. So call this V1 and call this V2. So these vectors are definitely not perpendicular to each other. But how do we find a vector perpendicular to V1? So let's say we let W1 be the same as V1, and let W2, let's just take the component of V2 that's perpendicular to V1. So that is V2 minus V2 comma V1 over V2, V2 over V1, V1, V1. Right? So if you go back and you look at our formula for finding the component of a vector perpendicular to another, the component of V2 parallel to V1 is V2 comma V1 over V1, V1 times V1, and V2 minus that. This should be the orthogonal complement. Let's actually do this calculation. Let's see what we get. So the inner product of V1 and V2, that's the inner product of the vectors 2, 1 and 1, 2. So that's 2 times 1 plus 1 times 2. That's 4. What is the length of V1? Or what is the inner product of V1 with itself? 2, 1, comma 2, 1. That's 2 times 2 plus 1 plus 1. That's 4 plus 1, and that's 5. So this is V2, which is the vector 1, 2, minus 4 over 5, that's scalar, times the vector V1. So that's 1, 2 minus 8/5, 4/5. And 1/2 minus this is 1 minus 8/5 is minus 3/5, and 2 minus 4/5, that's 10 minus 4 is 6/5. So we have W1 is 2, 1. W2 is minus 3/5, 6/5. And what is the inner product of W1 and W2? It's 2 times minus 3/5 plus 1 times 6/5. That's minus 6/5 plus 6/5 is 0. So W1 and W2 are perpendicular to each other. So they give us an orthogonal basis. But suppose we want an orthonormal basis. We want unit vectors. Well, all we do is, what's the unit vector computed from W1? The unit vector would be 1 over the length of W1 times the vector W1. The length of W1 is the square root of 5 times the vector 2, 1. So we get 2 over root 5 and 1 over root 5. So this is a unit vector in the direction of V1. What is U2? Well, we take 1 over the length of W2 times W2. What's the length of W2? So you square this, you get 9 over 25. This square this, you get 36 over 25. 9 plus 36 is 45. You get 45 over 25. Let's see. 45 over 25 is 9 over 5. So 1 over 9/5 is 5/9. Oops. Square root. Square root of 5 over 3. Right? For W2, this squared plus this squared is the length squared. So that's 9 over 25 plus 36. 45 over 25, or 9 over 5. So the square root is 3 over root 5. So 1 over the square root is root 5 over 3 times W2, which is minus 3/5, 6/5. So what we get for U2 is the vector. These 3's cancel. I get minus 1 over root 5 and 2 over root 5. So that's an orthogonal basis for R2 constructed from these two vectors. So in a little bit, I will post these notes and also some homework problems for tomorrow or whenever you can turn them in. That is just practice using what we've been talking about today, including the Gram-Schmidt orthogonalization process. That's where we are. Okay, I will quit for the day. That's the story.